In this surveying class, it is important that we consider significant digits. Significant digits have a very specific meaning when it comes to the way we describe the precision of our measurements. So since we're dealing with measurements all of the time, this is a very relevant discussion. So there is a proper way to express things and to express measurements. Again, the most important thing to remember is that we shouldn't over-represent the amount of precision you had when you took the measurement. So we talked in the past of how do you even make a measurement, we're going to be talking, or you have maybe already seen this, how to read a tape measure and all of that, and how to write the error, how to do a lot of things. However, it is important to know that we're going to be doing calculations with numbers, and that the number of significant digits that we report is very important. So the result should not be more precise than than what you used to calculate it. How many digits you need depends on what you're working towards. So one will depend on what, like, the kind of data that you were given. On the other hand, if you're the one making the measurement, how precisely you can read your, say, tape measure or whatnot. So, and depending on the amount of precision you require, there's ways to work around that so that you can have the proper number of digits. What do we even mean by significant digits? A significant digit is any digit of a number that is known with certainty, or any digit of a number beginning with the leftmost non-zero digit and ending with the rightmost non-zero digit, or a zero considered to be the exact value. Okay, so that probably sounded more confusing than it is. So in other words, significant digits is a quantity of meaningful digits in a number, and there are some general rules and examples that may help clarify this. So first of all, let's talk about, before I head over to the rules, let's talk about what am I even talking about, right? Okay, so let me make sure. Okay, so when I say that I measured, a table, and I found that it was 1.23 feet, it means that I was actually able to measure it with this much precision. So this here has 3 significant figures, 3 sig figs, or significant digits. Now, what if I tell you that I have, that my table is 1, and if I measured it, and it was actually 1.20. Now, we can agree that on the, like, when in practical sense, 1.2 and 1.20 are the same thing, right? However, if my table ended up being actually 1.20, and my mark, I was measuring with my tape measure, and it was like here, and the table was exactly, whoops, I missed that long, adding that 0 matters, because I am saying officially I was able to measure up to this precision, whereas here I'm saying I either couldn't calculate that digit, I couldn't read my tape measure that closely, or I am saying that this is a precision that I feel comfortable with, and I've already rounded. So if I see something like 1.2, this has a range. This could be anywhere as, if you think about it, in 2 sig figs, I could have had something like 1.16, or I could have 1.24. And even more than that, but it's just an example. This could even be like 1.15, etc., or 1.5 and more digits. Long story short, this is what I feel comfortable, or these are the digits that mean something, but it means that I have a range. If I give 1.20, that means that it could have been, so on the other hand, if I had 1.20, my range is now, well, it could have been 1. Let's see, so that would be one more digit, so like 199 or 2.203, etc. This is not the range, I'm just saying all of these fall within this. And now I realize that I've probably just confused you. So we're going to see the rules, and maybe it'll make more sense here in a second. Okay, so what is a significant digit? A significant digit is any number that is not a zero. So any number that is not a zero is significant. So if we have a number like 549, 1.892. Now remember that we're both talking here about measurements we are being given as well as measurements we make. So if you don't have zeros, all of your digits that are non-zeros are significant. Now, what if I have a zero trapped between two non-zero numbers? Then it is significant as well. So here we have, in parentheses, I put the number of significant digits. So 3 for this one, 4 for this one, 4 for this one. Even though it has a zero, that zero counts. Now, here's where it starts getting a little trickier. Zeros to the left of the first non-zero digit are not significant. That means that this number has only two significant digits. Now, you may be a little nervous thinking, well, obviously these digits mean something because 0.34 is not the same as 0.00034, right? Yes, you're absolutely correct, but that's not what significant digits is all about. What it's saying is I am sure of this number up to this many digits of precision, right? It doesn't mean that these two things are the same thing, and it doesn't mean that you don't need those zeros there, that they don't matter. What it means is that that you're sure up to that point. So in this case, this only has two significant digits, as opposed to, let's say that you were able to measure it with more precision. What if you had 340? Then this is 3. Or 0.00003400000. Now, this is an insane amount of precision, but let's say that this were the case. Now we have 1, 2, 3, 4, 5, 6, 7, and this is me getting ahead of myself because for numbers with decimal points, 0 to the right of the non-zero digit are significant. So this is what I was trying to say. If these are not going to contribute, but after that, they will. So in this case, if you have a whole number and a decimal point and zeros after that, those are significant. Each one of these counts. Now remember, we had that discussion. 2 is the same as 2.0 is the same as 2.00 for practical purposes, but not for significant figure discussions. Let me erase all this junk. There we go. So if we write that, that means that I mean it, that I was able to measure up to that point and with that much precision. In this case, look at this number, 0.050. The two significant digits are these two right here. Oops. Pen. These two right here, not that one. These are the three. All right, also for numbers without decimal points, trailing zeros may or may not be significant. So to indicate that the trailing zeros are significant, a decimal point must be added. So this is ambiguity. So if you have a number like 400, this can have 1 sig fig or 3 sig figs. And here it matters, I know they're to the left, but it is a number without a decimal point, or it's actually in the part before the decimal point. So 400 could mean could mean if I did not include these zeros, then that means that I could have that my range could be all the way to like 4. It would include things like 449, or as big as or as small as 351. Right? This rounds up to 400. This rounds down to 400. Whereas here with this, I know it doesn't seem to make a huge difference, but it does, because if I'm saying 400 period, I'm telling you I mean this, and now my range is actually, or my, the precision I have is this could be, let's see, for, trying to think, 0, 0. And then I would have to add another 400.4 or 399.4. 6 or something. So you see how this is different. It matters a lot, and it's not right or wrong in this case to do any of this. It depends on the data you were given or how you were able to do your measurements. Okay. So some advice, or well, actually I have some advice, but I also have some recommendation. What about when I have to do calculations with my digits? So when it comes to multiplication, division, you can only, let's say that I have two numbers, and let's say I have 2.03 times 1.2. I can only have as much precision as the number that has the least precision of my digits. So I can't jump ahead and say, let's say, and I'm doing this right now in my calculator, times 1.2. This gives me 2.436. Now, this is 3 sig figs. This one's 2. I can't have 4 in my answer. The max I can have is 2, because it's the smallest of all of the numbers involved. So what I do, all it means is I need to round this. So my answer would be 2.4. Same thing for division. Now, what if I have multiple calculations? So what if I have 2.03 times 1.2 divided by 0.6, I don't know, 95. Okay, so when I do these two numbers, I don't need, so let's say that I do that first, I don't need to round. So don't round before in intermediate calculations. Only round at the very end in your final solution. So keep all your digits, even though they don't really mean much, but they will, if you cut them, if you round early, you're going to increase the error margin in your final solution. So let me do this in my calculator real quick. Divided by 0.695. This gives me 3.50503,597. Awesome, right? Of course, these numbers are meaningless because the original numbers I had 3, 2, and 3. And even though this one looks to have 4 and this one looks to have 3, I don't keep 3. I look at the original data, and if I could only measure that one to 2 significant digits of precision, this one needs to be 2 significant digits, so this is 3.5. Great. Now, what about addition and subtraction? Well, you would think that it would be the same, but it's a little different. So sometimes it works out. Let's say that you have, let's say, my same two numbers, 2.03 plus 1.2. If I add this, I have 3.23. Now this one has 3 sig figs. This one has 2. So you're going to think, well, my solution should have 2. And you'd be correct. However, this won't always work out this way. There's a little bit of a difference with addition subtraction. With addition subtraction, we will use the numbers place, or what is that term called? Anyway, so it's more like, remember when this is like this is tenths and this is hundredths. Rather than sig figs, we're going to look at how far did I go into my, after my decimal point, and I'm going to keep up till the smallest one of these. So the last column, I don't have anything here, so I'm going to look here, and my answer should have only 1. So you're like, but isn't that the same? Well, let me show you an example. What if I'm adding 0.2, like 1,124.2 plus 2.365. Okay, so I'm going to do it over here. Actually, let me do it right here. In case you weren't confused enough, let me be super messy. Anyway, 1124.2 plus 2.365. So if I add this, actually this was a bad example because this has, no, it's a good example. So let's do this. So 5, 6, 5, 6, 2, 1, 1, right? Something like that. All right. So you might be thinking, well, this one has 4, 6, 1, 2, 3, 4, 5. Sorry, 5 sig figs. This one has 4, so I can keep 4. So now I'm going to end this with 1, 1, 2, 7. Okay. And this would not be the right way to do it. The right way to do it with addition and subtraction is to look at my places after my decimal point and say, well, this one has 1, this one has 3. I can only go 1. So I can actually have that extra digit here. So 1, 1, 2, 6, point, and I can have, well, 5, it's a 6 afterwards, so it's going to become a 6. There we go. So this would be the correct answer. So it's a little bit different than the rules for multiplication division. We're looking at number places, not sig figs per se, although sig figs, of course, are important. Okay, so let me erase something. So now, some advice: use an appropriate number of significant figures. In surveying, it will depend on your equipment. So some equipment, better equipment, can measure up to more precision, like a GPS unit, rather than, say, your steel tape. If you list a digit, you must mean it. And if you're not sure where the digit is significant, assume that it isn't. For example, if the direction of an experiment reads, add the sample to 400 milliliters of water, assume the volume of water is known to 1 sig fig. This also leads to a discussion about rounding. You saw me round a second ago, and I'm sure you're well acquainted with rounding, but just in case, quick summary. In engineering, you'll have to be careful with rounding, and mostly it's not that you wouldn't know how to round necessarily, but it's more about the concern for those intermediate calculations. So whenever we're rounding, let's say to 3 sig figs, we pick, so this would be my third sig fig, this is my target digit, and the digit next to it is going to be called the decision digit, which is going to tell me what to do with my target digit. So if your decision digit, if you're considering 3 sig figs, for example, is greater than 5, you round up. So if we have 352.8, 2 is my target, and 8 is my decision digit. 8 tells me it's higher than 5, so it tells me to round up, so 353. Here, 352.51. Well, 5, it's not greater than 5, but it is 5 with more digits. So 51 means I'm going to go up. And this one, you see, this one's my target. This is my decision. 6.37. Great. If it's smaller than 5, round down, pretty straightforward. So here, remember 3 sig figs doesn't count, the 0 doesn't count. So we have 1, 2, 3. It makes my 2 my target and 1 my decision. 1 is less than 5. So when I say round down, that means we just stay wherever we were. Now, this one's a tricky one. To avoid statistical bias, if you have 5 and nothing after it or all zeros, you're going to round to an even number. So, for example, if you have 63.250, this is my target, this is my decision, and there's a 0 after that. So, in this case, rather than round up, like you've probably been taught, you're going to stay. Because you want to stay at a even number. This one, 63.25, is the same situation. It has except it has nothing after it, but it still means you need to stay. Now look at this one, 63.15. We have a 5, we have nothing next to it, but because this number is odd, we want it to be even, so we're going to round up. So you see how these two numbers ended up being 63.2? I know that's a little odd, but it means that when you start rounding things to get averages, that you're not going to end up with a higher average. It really does, all it does is it avoids statistical bias. Oops. Okay, well, that's it for our discussion, and keep these things in mind when you are doing your survey work. And remember, don't start rounding in intermediate calculations. Do it, and don't start making decisions about sig figs till you're in your last step. All right.